So, how does a computer actually work? I mean, really work. Not the stuff you see on the screen, but the deep, kind of magical stuff happening inside the box. Well, we're about to find out, because we're going to build one. Conceptually, of course, starting from just a single tiny switch. Let's dive right in.
Okay, I'm gonna bet you've had a brilliant idea for an app or a game at some point, right? Maybe it's the next Tetris, something totally world-conquering. You can picture it all, every feature, every single button. But did you ever stop and think, what's actually happening underneath all of that? Because here's the crazy part. There's this huge gap, right? Over here, you've got your brilliant, creative ideas, your games, your apps, written in something like Python or Java. And then way over here, you have the actual machine, which is, well, it's pretty primitive. It only gets on or off, zeros and ones. That's it. It has no idea what a game is, or a user, or fun. So the real question is, how in the world do we bridge that insane divide?
Well, the solution is one of the most powerful, most elegant ideas in all of computer science. It's called abstraction, and you use it every day. Think about driving a car. You just press the gas pedal, right? You don't need to know anything about internal combustion engines or fuel injectors to make it go. That's abstraction. It's this brilliant idea of building things in layers, where each new layer completely hides the messy complexity of the one below. So to really truly get how this all fits together, we're going to do something a little different. We're going to take this journey, but in reverse. We're not starting at the top with our fancy app. No. We are starting at the absolute bottom with the simplest, most fundamental building block you can imagine. And we're going to build our way up, one powerful layer at a time.
All right, let's get into it. We're starting at the very, very bottom. So for a second, just forget everything you know about processors or memory. We need to go even simpler than that, way more fundamental.
Okay, say hello to the NAND gate. This little thing right here, this is our universe. It's our foundational atom. Think of it as just a tiny electronic switch. And here's the rule of the game. This is the only thing we're allowed to assume exists. And what's absolutely incredible, I mean, it sounds almost impossible, is that from this one simple component, we can build everything, the whole computer. So, what's our first step? Our very first act of creation? We take a bunch of these NAND gates and we start wiring them together in all these clever little patterns. And by doing that, we basically create a whole new toolkit for ourselves. We build about 15 other fundamental logic gates. You've probably heard of them, like AND, OR, and NOT. Just like that, we've turned our one single building block into a whole set of tools.
Okay, so now we've got our basic toolkit of logic gates. We're ready to climb up to the next layer of abstraction. And with these tools, we can build something really, really powerful, the computer's brain. This thing is called the ALU, which stands for Arithmetic Logic Unit. You can think of it as the computer's calculator. And you can already see abstraction at work, can't you? We're no longer thinking about thousands of individual NAND gates wired together. Nope. We now just see a single, neat component, a chip, a black box, that does one job. It performs all the math and all the logic our computer will ever need to do.
So having a brain that can do math is awesome. But it's pretty useless if it can't remember anything, right? A calculator with no memory? So our computer needs a way to store stuff. Data, instructions, it needs memory. Now, to build memory, we have to introduce a whole new concept, time. We do this with a ticking clock, basically a constant pulse that keeps everything in sync. This clock lets us build special circuits with our logic gates that can, latch onto a value and just hold it there. These little memory cells are called registers, and they can remember a single 0 or a 1. And you know what comes next? We combine thousands and thousands of these together, and boom, we've built the memory chips for our computer.
And this, right here, is where you really see the power of abstraction kick in. Once we've built our ALU, once we've built our memory chips, we get to completely forget about all those thousands of gates inside. We can just treat them as black boxes. We don't care how they work on the inside anymore. We only care what they do. Our job just got a whole lot simpler. All we have to do now is connect these boxes together.
All right, we've reached a huge milestone. This is kind of the climax of building our hardware. We have the brain, our ALU. We have the memory. Now it is time to put it all together and build an actual computer. And the process is just so elegant. We take our ALU black box and our memory black boxes and we wire them together to create the central processing unit, or CPU. Then we connect that core to the outside world, interfaces for a keyboard and a screen. And that's it. We've just followed a classic computer design called the von Neumann architecture. And what we have now is a complete hardware platform, a machine that's ready and waiting to run programs.
So, our hardware's done. It's built. We have this beautiful machine made of pure logic. But we still have that original problem, don't we? How do we get our big idea, our game, our app, to actually run on this collection of switches we've so carefully built? We need a bridge.
You see, this CPU we just created, it speaks its own language, a native tongue called machine language. And it's rough. It's just raw, unforgiving streams of zeros and ones. It's the only thing the hardware actually understands, but for a human, it's completely indecipherable, total gibberish.
And this is where the last crucial piece of the entire puzzle falls into place. We create a special program called an assembler. The assembler's job is to be our translator. It takes simple human-readable commands, words like add or store, and it translates them into those long, ugly strings of binary that our hardware can actually execute. This is it. This is the fundamental bridge that connects human ideas to machine action.
And there you have it. That's the entire journey, from the bottom all the way to the top. We started with a single atom, the NAND gate. From that, we built a toolkit of logic gates. From those gates, we built a brain and memory, the ALU and RAM. We combined those into a CPU, creating a computer. And then we built a translator, the assembler. And sitting right at the very top of this incredible pyramid of abstraction, that's where your idea lives, your game, your app. You know, this whole journey, from one tiny switch all the way up to complex software, it just shows you the incredible power of abstraction. And it kind of makes you wonder, doesn't it? What other really complex things in our world, in biology or in society, are built up in the exact same way? From simple, elegant building blocks, just layered one on top of the other, waiting for us to see the pattern.